Welcome to Module 10b in our series on artificial intelligence. This module, like the last, discusses backpropagation. More specifically, this module will present the math or calculus required to actually perform backpropagation with a step-by-step demonstration, and we're also going to take a look at some simulation results. Quick reminder, if you're interested in learning more about tensors or similar algebraic objects as a precursor or prerequisite to artificial intelligence, I do have this book that's available for purchase online. Before we discuss the math and calculus behind backpropagation, I did want to take 1 minute to review total and partial differentiation, the differences between them, as well as how the chain rule may be applied to either. So for that purpose, let's consider the system shown here. We have a function of two variables, two arguments, w and x, and then we have this sample definition where f of x is equal, or f of w and x is equal to 5w squared plus 3x. When we calculate the partial derivative df dw, and for the partial derivative, right, we employ what's called what I call the curly delta symbol. We assume that all other arguments or inputs aside from w, the one with which we are performing the differentiation, we assume that all other inputs are constant. We neglect any dependence x has on w, and as such, we end up with the partial derivative defined here, where the partial derivative of f with respect to w is equal to 10w, that's calculated by simply following the traditional rules of differentiation, plus 0. Now the reason why the second term is equal to 0 is because we are assuming that x has no dependence on w. A partial derivative of a multivariable function is differentiated with respect to only one of the arguments or inputs, with all others held constant or assumed to be held constant. When we calculate the total derivative, df dw, and for the total derivative we just use the traditional D script from English. So when we calculate the total derivative, we consider that x may depend on w. As such, we could represent x as a function of w. And so we end up with the total derivative of f with respect to w as defined below. Now the first additive term is the same because we're still applying the basic rules of differentiation. However, the second term is no longer equal to 0. It's equal to 3 times, so we're just keeping the coefficient. And since we don't know the exact relationship for this example between x and w, we can simply say it's 3 times the total derivative of x with respect to 0. So we can see the main difference between the partial and the total derivative is whether we consider this unknown relationship between x and w, or whether we consider all the other inputs to our function to be held constant. A total derivative of a multivariable function is the best linear approximation of that function with respect to all of its arguments and inputs. And again, just to repeat, we do consider that the following relationship, that x of w, may exist and is non-zero. Next, we apply the multivariable chain rule to both total and partial differentiation. For that purpose, we employ the system shown here. It consists of two functions, or two sets of functions. The main function, f, accepts 3 arguments, x1, x2, and x3. Those arguments, those variables, are then defined below the main function. So for all m, and we know that there are 3 elements of m, 1, 2, and 3, x superscript m is shown to accept a single argument w superscript, and that shouldn't be a k, that should be w superscript m. So what we see is that each argument is unique to its function. X superscript 1 is a function of w superscript 1, x superscript 2 would be a function of w superscript 2. The last relationship or dependency that we have to be aware of is that all of these w input arguments or variables have a direct dependency on time, and this same time variable is shared by all 3 of the x1, x2, and x3 variables. We may apply the multivariable chain rule to calculate the total derivative df dt as shown below. So let's say we want to calculate the total derivative of f with respect to time, but we're not able to define it explicitly from the functions shown above. One way to circumvent that is to use the multivariable chain rule to split this function into 3 parts. Why 3 parts? Why 3 additive terms? The 3 terms correspond to the 3 inputs or arguments to the main function f. Now each one of those additive terms, 1, 2, 3, may be decomposed into 2 factors that are multiplied by one another. The first factor is the partial derivative of f with respect to the current, in this case the first, argument to that function. So we have the partial derivative of f with respect to x1, and then the second factor for the first additive term is the total derivative of x1 with respect to time. And this pattern repeats for the other 2 terms, the partial derivative of f with respect to the second argument x2, and then the total derivative of x2 with respect to time, the partial derivative of f with respect to x3, and then the total derivative of x3 with respect to time. We may apply the multivariable chain rule to calculate the partial derivative df dw1, that's a mistake, I meant to put a 1 here, with the assumption that all the other arguments and inputs to the system remain constant, including w2, w3, and time. Now, here we illustrate one of the main differences between the partial derivative and the total derivative. The total derivative is performed with respect to t, this fundamental input variable that has an effect on all the intermediate w arguments as well as the intermediate x arguments or inputs. The partial derivative does not do that, right? We are performing that derivative with respect to a single variable, assuming that all others are constant. Now, for this system, if we're going to apply partial differentiation, we must neglect the effect of time on all of the w variables, because as it's defined, w superscript 1 cannot change without t changing, right? If we look at this representation here. However, for this second part of the page, we're going to neglect this relationship. And what we see is that the partial derivative of function f with respect to variable w superscript 1 is again broken up into three additive terms, 1, 2, and 3. This corresponds to the three inputs to the main function. The structure is pretty much the same as what we see up above for the total derivative in terms of we have df, partial derivative of f, with respect to x1. These two are exactly the same. And the main difference between this product here and this product is that above we have a total derivative and below we have a partial derivative, and that essentially repeats as we move to the right. So what we see is up above, the second factor for each additive term is a total derivative, and down here we see that the second factor for each additive term is a partial derivative. And to reiterate before moving on, the chain rule is advantageous because it allows us to calculate certain partial or total derivatives without making excessive substitutions. So for example, we can calculate the total derivative of f with respect to t without having to substitute in, so we have x1 is a function of w1 is a function of t, and having to do that for all of the inputs or arguments to function f. It also allows us to perform these derivatives when some practical limitation exists, and that allows us to perhaps perform or observe these relationships to perform these partial or total derivatives individually, but maybe that prevents us from performing the partial or total derivative as a whole. Next, we can discuss the math or calculus behind applying backpropagation to an output layer. We are going to present a step-by-step process here. After that, we'll move on to discussing how backpropagation may be applied to one or more hidden layers. Note that this module, 10b, is a direct follow-up to the previous 10a. As such, it employs the same example, the same neural network model shown here, as well as the same training data. It accepts two inputs referred to as x1 and x2, and generates two outputs referred to as x5 and x6. X superscript 5 with no subscript refers to the calculated or estimated value of this output as generated by the neural network. Its corresponding ideal value is represented by x subscript IDE with the same superscript. The output layer is composed of two nodes, both of which employ a sigmoid activation function and are connected to states x3 and x4 via four output layer synapse weights. We have W35, W46, we have W36, and W45. There are two neurons associated with the hidden layer, both of which employ a rectified linear unit activation function. They are connected to inputs x1 and x2 via four hidden layer synapse weights, W13, W24, W14, and W23. To properly apply the chain rule to backpropagation, as is the objective of this module, we must clearly define all of the functions relevant to this neural network, as well as the inputs or arguments that they accept. Remember that this module is a continuous of the previous, and we're using the same four-node neural network example from that module for this one. So we have four functions that we're going to look at. The first is a single component of the error. Now, if we remember from the last module, we saw that there were two components of our error. There's E5 and E6. E5 is associated with the state of output node 5. E6 is associated with the state of output node 6. So E superscript M is a function of two arguments, the ideal state of node M as well as the calculated or estimated state of node M. And here we can see the error function defined by the mean squared error. The second function type is the total error. The total error is merely the sum of the two relevant components E5 and E6. Each one of those function components accepts two inputs, so the total error accepts four inputs: the ideal state of nodes 5 and 6, as well as the estimated or calculated state of nodes 5 and 6. The third function that we need to review is the state of an output layer neuron, or an output layer state. So what we see is X superscript M, the state of node M, is dependent on 6 different values. We have all 4 of the output layer synapse weights, which we can represent collectively as W subscript OL, as well as both of the states that feed into the output layer, which I represent here as X subscript OL. The fourth type of function we need to look at is the state of a neuron in the hidden layer, or a hidden layer state, still represented by x superscript m, still a function of 6 arguments, but these arguments are different. So instead of it being defined in terms of the output layer synapse weights, we define them in terms of the hidden layer synapse weights, and instead of being defined in terms of x3 and x4, the states that feed into the output layer, we define it in terms of x1 and x2, the inputs that feed into the hidden layer. Next, we dive into the actual backpropagation process. Specifically, we want to define the gradient of the total error with respect to a synapse weight in the output layer. We'll deal with the hidden layer in a second. We begin with step number 6. Why step number 6? Because the last module, and this module is a continuation of the last, it performed the beginning of the backpropagation process. It defined the example we're going to use, it defined the neural network model, it defined the initial conditions of all the synapse weights, and it performed what we call the forward pass, which yielded all the network states and errors associated with a training data sample. Now in step number 6, we want to define the gradient of the total error with respect to an output layer synapse weight. We are going to employ synapse weight 3, 5, the synapse weight that bridges nodes 3 and 5 as an example, and then later we can generalize that to all the synapse weights in the output layer. We see that the total error is defined as the sum of 2 components, at least for our example, e superscript 5 and e superscript 6. Therefore, when we want to calculate the partial derivative of the total error with respect to a synapse weight, W35, we can apply that derivative individually to both of those additive components. We take the partial derivative of E5 with respect to W35, as well as the partial derivative of E6 with respect to W35. Now, if we go back and look at our neural network structure, we'll see that this partial derivative is equal to 0 and goes away because W35, that synapse weight, that synapse connection, does not interact directly with X6, and therefore it doesn't have an effect on E6. So what we see is that the partial derivative of the total error with respect to our synapse weight is equal to the partial derivative of just error component 5 with respect to that synapse weight. Now, we're left with a problem because we cannot explicitly define this partial derivative, at least not the way our functions are defined. So we move on to step 7, and we apply the multivariable chain rule to split this partial derivative up into components that hopefully we do know how to define. Now, the application of the chain rule depends on the specific definition of the function we employ, and so let's repeat that here. Previously, we defined function error component em as a function that accepts 2 inputs, 2 arguments. We have the ideal state of node m, in this case talking about node 5, as well as the calculated or estimated state of node m, in this case node 5. And so when we apply the chain rule to the partial derivative of E5 with respect to W35, we end up with 2 additive components corresponding to the 2 inputs accepted by this function. The first term has 2 factors. We have the partial derivative of E5 with respect to x subscript IDE. So how is the error component E5 affected by the ideal value, the ideal state of node 5, and then multiplied by the partial derivative of this ideal state with respect to synapse weight 3, 5. Now this component is equal to 0. It goes away because the ideal state is a constant value and is not dependent on the synapse weight at all. The second additive component, however, is not equal to 0. It has 2 factors, the partial derivative of error component E5 with respect to state x5 times the partial derivative of state x5 with respect to synapse weight 3, 5. Now we know that this state here is dependent on a weighted sum that is defined in terms of W35. As such, this partial derivative is not equal to 0. What we end up with is this observation that the partial derivative of the total error with respect to our synapse weight is equal to the partial derivative of only error component E5 with respect to the synapse weight, which then can be broken up into 2 factors, right? One shown in blue, which we'll calculate on the next slide, and another shown in green that we're going to calculate on the next slide. Step 8 attempts to define the partial derivative of error component E5 with respect to state x5. Note that this value, this partial derivative, is shown in blue on the last page. Now, for this step, there's no need to apply the multivariable chain rule, as we can define this partial derivative explicitly. We know that the loss is defined by the mean squared error function, and we can differentiate this with respect to x5. We take this exponent and move it out front. It becomes a coefficient of 2, which cancels out our 1/2. We can't forget about the -1 coefficient of x5. That moves out front, yielding this result here, -1 times the difference between the ideal state of node x5 and the estimated or calculated state of node 5. Now, one thing to note here is that the superscript index IT nor the sample number, neither one of those are used for this equation. We're not going to use them when it's unnecessary. So, for example, all of the values in this equation should be associated with a single iteration as well as a single sample. Note that in this module we stopped using the variable y. Previously we had referred to the ideal state of node 5 as the ideal output with an index of 1, and we had referred to the calculated or the estimated state of node 5 as y sub est superscript 1, but we're no longer using those variables because we can simply rely on the ones that are already defined by our neural network. Step 9 attempts to define the partial derivative of state x5 with respect to synapse weight 3,5 via the single variable chain rule. Note that this value, this partial derivative, is referenced in green 2 pages back. Okay, we want to define this partial derivative, and so as part of that we define state x5 within these parentheses. What we see is that state x5 is defined by applying a sigmoid activation function to a weighted sum h5. Now we can use the single variable chain rule to split this derivative up into 2 parts. We have the partial derivative of x5 with respect to h5, again, remember h5 is this weighted sum, times the partial derivative of the weighted sum with respect to synapse weight 3,5. One component is shown in red, the other component is shown in purple. We're going to focus on the purple for a second and then come back to the red. Differentiating the weighted sum with respect to synapse weight 3,5, again as shown here in the purple, is pretty straightforward. The second additive component goes away because it doesn't have any w35 in it, and we're just left with the first component, and we know that the derivative of this will simply be its coefficient. So in the purple, the partial derivative of the weighted sum h5 with respect to synapse weight 3,5, the result is simply state x3. Then we can move on to differentiating state x5 with respect to weighted sum h5. That's the same as just finding the partial derivative of the activation function. We use the identity shown here. The derivative, or same as partial derivative in this case, of 1 over 1 plus e to the negative h is equal to e to the negative h over 1 plus e to the negative h squared. And so we apply that identity here in red, and we're left with the result. Essentially, the partial derivative of state x5 with respect to synapse weight 3,5 is equal to e to the negative h over 1 plus e to the negative h times state x3. Now, I know some of you may be trying to follow this derivation and perhaps having a little bit of trouble. The best advice I can give is to try to go through by hand each step of this derivation process on your own. Now we know all the values required to define the partial derivative of the total error with respect to our target synapse weight 3,5. We saw previously that that was equal to the partial derivative of error component 5 with respect to that same synapse weight as presented down here. Now we can substitute back in those known values. So we know that this partial derivative can be decomposed into 2 products. One is shown in blue. It's the partial derivative of error component 5 with respect to state x5. We substitute that in. The second is the partial derivative of state x5 with respect to synapse weight 3,5, and we substitute that in. Step 10 presents the result of this substitution. Again, we see that the partial derivative of the total error with respect to our target synapse weight 3,5 may be decomposed into 2 factors multiplied by one another, one in blue, one in green. The previous page demonstrated these substitutions. Now the one note I want to make here is that everything in the green may be simplified to x superscript 5 times 1 minus x superscript 5. So the state of node 5 times 1 minus the calculated or estimated state of node 5. Moving from this first line to the second, we can simplify. This is equal to this, and what we see in its simplified form is that the partial derivative of the total error with respect to our target synapse weight 3,5 is equal to minus 1 times the difference between the ideal state of node 5 and the calculated or estimated state of node 5 times x5 again times 1 minus x5 times x3, where x3 is the state of node 3. Step 11 generalizes this relationship, this partial derivative, for any output layer synapse weight, of which there are 4. We've been talking about synapse weight 3,5. We also have to deal with synapse weight 4,5, 3,6, and 4,6. What we can see is that all 4 of these expressions, all 4 of these functions employ a similar form. For all of them, the superscript associated with the synapse weight is employed here, 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 and here. So we can see for W35, all of these superscripts are 5s. If we look down here at the partial derivative of the total error with respect to synapse weight 4,6, all of these superscripts are 6s, 1, 2, 3, and 4. This superscript shown in blue comes from the subscript of the synapse weight. As such, we see that a 3 is used here, same as the 3 used here in the subscript. If we go all the way to the bottom, we see that this superscript corresponds to the subscript shown to the left, and these two follow a similar form. Now this is great for the output layer, however, we do have a problem. We'll see that there's a problem. We cannot apply this same process to the hidden layer synapse weights. And the reason is because the effect of these weights, of these hidden layer synapse weights, on the output x5, x6, as well as the error e5, e6, is more complex and more indirect. Now that we've successfully applied backpropagation to the output layer, calculating the partial derivative of the total error with respect to all the synapse weights in that output layer, I want to ask, what is the overall strategy for applying the chain rule in backpropagation? Essentially, the chain rule allows us to decompose unknown derivatives into smaller and more granular components until hopefully all of those components may be explicitly defined. Next, we explore how to apply the backpropagation algorithm to a hidden layer to calculate the partial derivative or gradient of error with respect to the synapse weights that reside in that hidden layer. And again, we're going to be presenting this as a step-by-step process. We begin our derivation of how to apply the backpropagation algorithm to a hidden layer similarly to how we began when applying it to an output layer. We need to define the gradient of the total error with respect to a hidden layer synapse weight. Now, we're going to consider synapse weight 1, 3 that connects nodes 1 and 3 as our example, and we're going to use it similarly to how we used synapse weight 3, 5 as part of our derivation for the output layer. Now, unlike the output layer case, one of the two terms of error, E5 and E6, is not necessarily going to disappear. If you remember, when we defined the partial derivative of the total error with respect to synapse weight 3, 5, what we saw was that this only had an effect on E5 and didn't have any effect on E6. As such, we ended up with the second term going away. That's not going to be the case, or not necessarily going to be the case, for the synapse weights associated with the hidden layer. Now, why is that? Let's take a look at synapse weight 1, 3, right? It connects state 1, or node 1, to node 3. Node 3 is then similarly connected to node 5, as well as node 6, and then that in turn generates the error component associated with that node, as well as the error component associated with node 6. Here we have synapse weight 3, 5 and synapse weight 3, 6. So what we can see here is that this synapse weight 1, 3 has a very pronounced effect on both the component E5 as well as component E6 of the total error. And as such, one of those two terms, the E5 or E6 terms, is not necessarily going to disappear unless one of these synapse connections is removed for some reason. So returning to this equation, we see that in order to calculate the derivative of the total error with respect to synapse weight 1, 3, we need to calculate a similar derivative between the component E5 and our synapse weight, as well as error component E6 and our synapse weight. Later, we will have to generalize this solution for all hidden layer synapse weights, but that's similar to what we did for the output layer as well. Step 13 attempts to apply the partial derivative multivariable chain rule to define the relationship between error component E5 and hidden layer synapse weight 1, 3, as well as error component E6 and that same hidden layer synapse weight. We should note again that application or proper application of the chain rule requires us to have a clear understanding of how these error functions are defined. Previously, we demonstrated that error component 5 accepts two arguments: the ideal state of node 5, we could also refer to that as the ideal output of node 5, as well as the estimated or calculated state of node 5. Now, the reason why we need to apply the multivariable chain rule is because we don't have a good way of explicitly defining this partial derivative. As such, we use the multivariable chain rule to divide it up into two additive components. Why two components? Because we have two arguments supplied to our function. I'm going to skip some steps here because we've done similar derivation several times. The first component essentially goes away because the ideal state of node 5 is not dependent on this synapse weight, so this component goes away. The second remains, and it's decomposed into two factors: the partial derivative of error component E5 with respect to state x5, as well as the partial derivative of state x5 with respect to our hidden synapse weight 1, 3. Taking away this component, we're simply left with what is shown in the gold. We can apply the multivariable chain rule in almost the exact same manner to calculate a similar result for the partial derivative of error component E6 with respect to that same hidden layer synapse weight 1, 3. Fortunately, two of those factors are already known. We define them as part of our derivation for the output layer, so we can revisit step 8 from that part of the derivation and observe that the partial derivative of error component E5 with respect to state x5 is known, and it's equal to -1 times the difference between the ideal state of node 5 and the estimated or calculated state of node 5. We have a similar expression below that. The partial derivative of error component E6 with respect to state x6 is equal to -1 times the difference between the ideal state of node 6 and the estimated or calculated state of node 6. Again, we already know these partial derivatives, so there's really no need to recalculate them. And if we jump back one page for a second, we see that 2 of these 4 unknown partial derivatives are now known. Essentially, we know the partial derivative of error component E5 with respect to state X5, and we know the partial derivative of error component E6 with respect to state X6. That just leaves 2 more unknowns, the partial derivative of state X5 with respect to our hidden layer synapse weight, and the partial derivative of state X6 with respect to our hidden layer synapse weight. So our last task, or our next task, is to define both of those. As such, step 14 attempts to employ the partial derivative multivariable chain rule to define the partial derivative of state X5 with respect to hidden layer synapse weight 1,3. I don't know why I neglected to use the curly delta symbol there, as well as the partial derivative of state X6 with respect to that same hidden layer synapse weight. Now we need to apply the multivariable chain rule because we can't define this partial derivative explicitly, at least not in its current form. Again, we should remember that proper application of the chain rule requires us to have a clear understanding of the function as well as the arguments that it accepts. Here we have our definition, previously stated in the presentation, of the state of a neuron within the output layer of our neural network. It's dependent on 6 arguments, 4 of which are the synapse weights associated with the output layer, and 2 of which are the states that feed into the output layer. Therefore, when we apply the multivariable chain rule to this partial derivative, we expect to see 6 additive components. Now, 4 of those, essentially those associated with the output layer synapse weights, will go away. Why? Because the partial derivative of any synapse weight within the output layer and any synapse weight within the hidden layer, for example synapse weight 1,3, that relationship is equal to 0. There is no dependency between those two. As such, this term goes away and we're left with 2 remaining terms. The second term disappears because the partial derivative of state X4 with respect to hidden layer synapse weight 1,3, right, that equals 0. That synapse weight is not associated with state X4, leaving simply this term, which is then copied over here. We can apply a similar derivation, a similar simplification to the partial derivative of state X6 with respect to hidden layer synapse weight 1,3. Again, what we see is that the partial derivative of any synapse weight in the output layer, right, it has no relationship to the synapse weights in the hidden layer. This first set of 4 terms will disappear. We'll be left with 2 terms. We see again that the state of node 4 is not dependent on synapse weight 1,3, leaving merely this term as shown to the right. Now, one question that I want to ask is, why can't we calculate these derivatives directly as done in step number 9 as part of our derivation for the output layer? And the answer to that question is that unlike the output layer, the hidden layer synapse weights don't have a direct effect on the network outputs X5 and X6, nor a direct effect on the error components E5 and E6. Step 14 demonstrated that we need to define the partial derivative of state X5 with respect to state X3. We yield state X5 by applying the sigmoid activation function to the weighted sum H5 shown in blue. Now, we could perform this differentiation in a single step. However, in order to make the process a little bit more straightforward, a little bit more digestible, we'll apply the single variable chain rule and split this up into 2 factors. The first is the partial derivative of state X5 with respect to the weighted sum. The second is the partial derivative of that weighted sum with respect to state X3. The term in red is merely the partial derivative of the activation function. We'll deal with that in a second. Let's first focus on the factor in purple, which requires us to take the partial derivative of weighted sum H5 with respect to X3. This is pretty easy to do. We see we have 2 additive terms. The second one does not employ X3, so we merely need to take the partial derivative of the first term, and that is going to be the coefficient W35. Now we deal with the factor in red, and that requires us to take the partial derivative of the activation function, and we already demonstrated earlier that that would be equal to state X5 times 1 minus state X5, and then we tack on to that the weighted sum 35. Step 15b asks us to merely repeat this differentiation above in order to define the partial derivative of state X6 with respect to state X3, and it yields a result in a very similar form. State X6 times 1 minus state X6 times synapse weight 36. Jumping back to step 14 for a second, we saw previously that there were 4 partial derivatives we needed to define. Actually, not 4, because this and this are the same, so that brings the 4 down to 3. In step 15, we defined this partial derivative as well as this partial derivative, which leaves only a single partial derivative we need to define in order to reach our ultimate goal. In step 16, we attempt to define that final missing partial derivative, the partial derivative of state X3 with respect to synapse weight 1,3. I apologize, I don't know why I neglected to use the curly delta symbols here. So, in order to calculate this partial derivative, first we need to understand that state X3 is yielded by applying the rectified linear unit activation function to the weighted sum H3. Now, how does the rectified linear unit function work? Essentially, this activation function yields its input. If that input is greater than or equal to 0. It yields a value of 0 if its input is less than 0. Now, we're not interested in the actual value here, we're interested in the partial derivative of that with respect to synapse weight 1, 3. If the weighted sum, if the input to the activation function is less than 0, we need to take the derivative of 0, and so that's 0. If the input, the weighted sum h3 is greater than or equal to 0, we merely need to take the partial derivative of the weighted sum with respect to synapse weight 1, 3. That's pretty easy to do. We have two additive terms. The second term has nothing to do with w13, as such we can eliminate it, and then we take the derivative or the partial derivative of the first term, and we're left merely with the coefficient of synapse weight 1, 3, which is x1. So right here we have the partial derivative of the weighted sum with respect to synapse weight 1, 3 when that input is greater than or equal to 0, and that same derivative is equal to a 0 when the corresponding value is also equal to 0. So we define this partial derivative of state x3 with respect to synapse weight 1, 3. Below it I present the partial derivative of state x3 with respect to synapse weight 2, 3. Now we don't need this value yet, but we will need it later when we attempt to generalize this result for all synapse weights in the hidden layer. We now know all the values, all the partial derivatives required to achieve our ultimate goal, to define the partial derivative of the total error with respect to hidden layer synapse weight 1, 3. All that's left is to make the appropriate substitutions. In step 14, we demonstrated that the partial derivative of state x5 with respect to synapse weight 1, 3 is equal to the product of these two terms, one shown in green, one shown in purple. Note that these colors don't necessarily correspond to the colors used in previous pages, and we already know the value of these factors, so we can make the appropriate substitution, and repeat this process for the partial derivative of state x6 with respect to hidden layer synapse weight 1, 3. We continue this substitution process by revisiting step 13. Step 13 demonstrated that the partial derivative of error component E5 with respect to synapse weight 1, 3 is defined as the product of these two factors, one shown in red, one shown in blue. Note that the factor shown in blue is the one that we defined on the very last page. Again, all we have to do is make the appropriate substitutions, taking those values from the previous pages, and we can define the partial derivative of error component E5 as well as the partial derivative of error component E6, both with respect to the hidden layer synapse weight 1, 3. We know, for this example at least, that the total error is equal to the components E5 and E6. We can apply that same rule to the partial derivative. We showed this previously. So the partial derivative of the total error with respect to synapse weight 1, 3 is equal to the partial derivative of component E5 taken with respect to that, plus the partial derivative of component E6 taken with respect to that. Now, I don't think I need to show these results again because we just defined them on the previous page, right? The piecewise behavior came from the rectified linear unit activation function. Next, we simplify. We essentially put all of the terms onto a single row. The really only major change is shown in green, where we replace these if-else statements with the unit step function, accepting the weighted sum h3 as its input. Now, how does the unit step function work? Essentially, it yields a value of 0 whenever the input, h3, is less than 0. However, when it equals 0, it jumps up to 1 and spits out a value of 1 for any value, any input value greater than or equal to 0. So essentially, by multiplying x1 by this unit step function, it behaves the same as these if-else piecewise functions did. Finally, step 17 allows us to bring together both halves, both parts of our derivation, dealing with both the output as well as the hidden layers. Essentially, it presents generalized expressions for the gradients or partial derivatives required to perform gradient descent as used for supervised machine learning. This supervised machine learning process optimizes the synapse weights, calculates synapse weights which minimize the difference between the ideal and the estimated or calculated outputs, as well as in turn allow our neural network, remember we're still dealing with our 4-node example, allow our neural network to mimic the ideal observed behavior that is defined within the training data. We have two generalized expressions, one for the output layer, which defines the partial derivative of the total error with respect to synapse weight km. Now remember, if this is in the output layer, then we know that node m is also in the output layer. So that's defined as -1 times the difference between the ideal value yielded by output node m minus the calculated or estimated value times the calculated value times 1 minus the calculated value, and then times the calculated value of not the destination node, but the origin node k. The generalized expression for the hidden layer is a bit more complex if we attempt to define the partial derivative of the total error with respect to synapse weight km, where at least for our example we only have a single hidden layer. So what that means is that node m we know is in the hidden layer and node k would be an input. And so that's equal to -1 times the ideal output generated by node 5 minus the calculated times the calculated, and so on and so on. I don't think I need to read through all these terms as we just did it for the previous page. Fortunately, that ends our derivation. The last thing that I wanted to do in this module was to present an Excel-based demonstration of how we can use those generalized update expressions to perform gradient descent, to apply that to supervised machine learning, and to essentially optimize the example 4-node neural network that we presented in the previous module. For this demonstration, we employ Microsoft Excel to implement the generalized update expressions from the last page, right? We use those update expressions to perform gradient descent as required for supervised machine learning, and we're applying supervised machine learning to optimize the synapse weights within our example 4-node neural network, the one that was designed to perform recognition of the handwritten zeros and ones. Now, the spreadsheet for this demo is downloadable. You can use either these text links or the QR codes, and for the sake of redundancy, I provide versions that are downloadable from Google Drive as well as Dropbox. Here we have a screenshot of the Excel worksheet. I'm going to try to go through and highlight the most important parts. However, if you want to gain an in-depth understanding of how this works, I recommend that you download the worksheet and play around with it. So we begin with the first column. This shows the iteration number. Of course, it starts with iteration 0. The second column demonstrates or shows which training data sample is associated with that iteration. We're still using single element stochastic gradient descent, so there's a single training sample that's associated with each iteration. We then have to the right of that the input states x1 and x2 associated with that sample. To the right of that, we have the ideal labeled outputs associated with that sample. This tells us whether the handwritten digit is supposed to be a 0 or a 1. To the right of that, we calculate from the x1 and x2 values, we calculate the weighted sum for nodes 3 and 4. We then apply the activation function to generate the output or the state of those nodes. We do the same thing for the output layer, nodes 5 and 6. We calculate the weighted sum as well as apply the sigmoid activation function. Now, to the right of that, in the green, we use the generalized expressions that we derived in this module in order to calculate the gradient or the partial derivative of the total error with respect to the hidden layer synapse weights. So here you can see derivative of total error with respect to W13, W23, W14, W24. To the right of that, we have the actual synapse weight values. Now, the reason why the first row is highlighted in red is because that would be the initial condition of those values, but as we move forward, what we would do is use the gradients in order to update them. So that's the reason why you see these synapse weight values changing as we move downward. To the right of that, we calculate the derivative of the total error with respect to the output layer synapse weights. Then we have the output layer synapse weights themselves. And finally, in the green, we calculate the total error as well as the two error components E5 and E6. The black boxes serve as sort of a flowchart to demonstrate how this worksheet operates. Above the red line, we have the part of the flowchart that deals with evaluation. It essentially takes the inputs yielded by the training data and calculates the state of our 4-node neural network. Below the red line, we have the part of the flowchart that performs the update. So we begin over here on the left in this red column, hence why the box is in red. We load the appropriate training sample. We then move over to the box in yellow where we calculate the states or states of the hidden layer. We then calculate the state or states of the output layer. We calculate the appropriate error or loss by comparing these states to the ideal values. After that, we calculate the hidden layer gradients, right? The partial derivative of the total error with respect to the hidden layer synapse weights. We do the same thing for the output layer. And then finally, we take those gradients, we combine them with the previous values of the synapse weights, and we update the output layer weights as well as update the hidden layer weights. After that, we simply increment the iteration and start over. Here we can see simulation results for our stochastic gradient descent. So we are going to talk about batch versus stochastic gradient descent as part of the next module. The only thing you really need to know for now is that since we're employing stochastic gradient descent, that's why we only have one training sample associated with each iteration. Now, for both of these graphs, the x-axis is the iteration number. For the top graph, the y-axis actually presents the synapse weight value for all 8 of the synapse weights. So here we have the hidden layer synapse weights. Here we have the output layer synapse weights. They start out with their initialized values and then eventually migrate to their final values. The bottom graph, again, x-axis is iteration number and y-axis would be the mean squared error. So at the time of initialization, the error is relatively high, but we can see that the training works because by the time we get to the end, the 90th or 100th iteration, the mean squared error is pretty low. And what that means is that we've optimized our synapse weights, that supervised machine learning has at least in part succeeded, and we've ended up with the 4-node neural network that is able to somewhat accurately differentiate between the handwritten 0 and 1 symbols. This module presented the math and calculus required to perform backpropagation step by step. I think it was a great complement to the previous module, which focused more on visualization. In this module, we also provide the Excel-based simulation file that essentially demonstrates or proves that those generalized update expressions we derived, well, that they work. Watch the next module to wrap up our discussion of gradient descent and backpropagation. With focus on complete batch versus stochastic gradient descent, we're finally going to make that differentiation, as well as a pretty robust discussion of hyperparameters and how they affect machine learning performance. I do provide a homework assignment for this module. I'll post a solution after we get at least 10 responses in the comments. I ask you to define your own supervised machine learning problem with 2 inputs and 2 outputs. Some examples include an alternative handwriting recognition case. You could use potentially different sensor placements even. You could employ an or/and Boolean gate, or really any system that maps 2 inputs into one of 2 categories. So any binary classification example with 2 inputs. I ask you to modify the provided Excel spreadsheet to train a 4-node neural network to mimic that behavior which you propose. Now, you may need to do several things. You may need to adjust the learning rate or the maximum number of iterations. You may need to reset and change the initial conditions. And you may need to manipulate the hyperparameters or introduce new hyperparameters in order to achieve the performance that you're looking for.